Welcome back. This is the last vector addition video, and I'm going to discuss the equilibrant of vectors. So when will vectors be in equilibrium is the big question. They are in equilibrium when the resultant vector is 0. So let's look at an example. This is you. You are busy sitting on a chair. So there is a force of gravity on the chair. Let's say the force of gravity is 500 newtons. The chair is pushing back on you. So the chair's pushing force, the force of the chair on you, will it be equal to, smaller than, or bigger than the gravity, the force of Earth on you? Well, if the force of the chair on you were bigger than gravity, you'll be moving up. If the force of gravity is bigger than the force of the chair on you, you'll be moving down. No, you're sitting still, you're not moving anywhere. So the chair pushes back on you with a force of 500 newtons. We can see that the forces are acting in opposite directions. So I'm going to choose my gravitational force's direction as positive. Then the chair's force on you will be the negative direction. So the net force on you will be Fg plus Fj. So it is the 500 minus the 500. So the net force acting on you is 0 newtons, meaning that the two forces, gravity and chair, is in equilibrium. The resultant is 0. What is the equilibrant is the next question. Now the equilibrant would be the force that keeps two or more other forces in equilibrium. We're going to discuss an example now. So it is the vector that has the same magnitude but opposite direction to the resultant. Right, we've got a tree, and we've got two elephants pushing against this tree. So it's the force of the one elephant, let's say it's 1,000 newtons, and the force of another elephant, let's say that is 500 newtons. So this tree is not going anywhere. It's not breaking, it's not moving, nothing. So what is the force of the tree in the opposite direction? What is the force of the tree is the big question. Now that force will keep F1 and F2 in equilibrium. The question is, what is the size of that force? So let's first get the net force here. It's the force of the first elephant plus the force of the second elephant. So it's 1,000 plus 500. 1,500 newtons, and in our diagram it's to the right. So what must the force of the tree be? The force of the tree is the equilibrant, and it will be 1,500 newtons to the left. So the force of the tree is the equilibrant, and it's equal in size to the resultant force, and it's opposite in direction to the resultant. It keeps the two forces F1 and F2 in equilibrium. Right. Use the head-to-tail method to determine the resultant force of a car that needs to be kick-started by two men pushing at the back with forces of 50 and 45 newtons respectively. You can choose your own suitable scale, where 1 centimeter will, for example, represent 10 newtons, and go for it, practice. Now, algebraically, I can see they're going in the same direction, pushing at the back. So 95 newtons will be the resultant force. So what will the equilibrant of these forces be? So it will be 95 newtons forward. What will the equilibrant be? It will be 95 newtons backwards. Right. Next, we use the graphical head-to-tail method to determine the resultant force of a rugby player if two of his teammates are pushing him forwards with forces of 60 and 90 newtons respectively, while two opponents are pushing him backwards with forces of 165 newtons respectively. Please choose a suitable scale. Try this by yourself. I'm just going to draw a rough diagram here. So this is the rugby player, and his teammates are pushing with forces of 60 newtons and 90 newtons. They're pushing him forwards. He's got some opponents acting on him, so they're going in the opposite direction, 100 newtons and 65 newtons. So algebraically, if net, now you need to choose which is your positive and which is your negative direction. I'm going to choose it like this. So algebraically it will be 90 plus 65 minus 100 minus 90 plus 60 minus 100 minus 65. So if I chose my positive and negative direction like I did, I will get a negative answer here, negative 10, negative 15 newtons. This needs to be explained, so it is 15 newtons backwards. Okay, what is the equilibrant of these forces? The equilibrant is the same size as the resultant, but opposite in direction, so it is 15 newtons forward. So technically speaking, the rugby player needs to help his teammates to push forward with a force of 15 newtons if he wants to stay in the same spot. And that will mean that all the forces acting at that point will be in equilibrium. Next, a man applies a force of 5 newtons on a crate. The frictional force on the crate is 2 newtons. So here I need to know that if somebody applies a force of 5 newtons, we can call this F applied. The frictional force will always act opposite. So friction is 2 newtons. They're in opposite directions. I'm going to choose that applied force, the positive direction, then the friction would be negative. That calculate algebraically. So F net is the friction plus F applied, and it will be minus 2 plus 5, so it is 3 newtons to the right if I look at the diagram like it is. B's answer, what will keep these two forces in equilibrium? The equilibrant will be 3 newtons to the left. Right.